Good day, I'm J Wildberger. Today we're going to continue looking at on sequences. This is our attempt to slowly focus on so-called infinite sequences, but rather in a more careful and precise way than you're going to find anywhere else. The notion of a sequence, especially an infinite sequence, is not a God-given one. It's not one that we are born to understand. It does not drop on our laps. We need to work to build up such a notion, and we must be very careful not to fall into certain traps. So last time we talked about polynumber on sequences, where we start with a polynumber or a polynomial. For example, p equals 1 plus alpha plus 2 alpha cubed. And from that we can generate a so-called polynumber on sequence. And I remind you, this is the notation that we used. We used a square left bracket and a pointed right bracket. We used the letter n, so we replaced the alpha in the polynumber with the letter n. And that for us signifies a polynumber on sequence. And this particular sequence represents the numbers 4, 19, 58, 133, 256, and so on. Just the values that we obtain by replacing the n here with first of all 1, and then 2, and then 3, and then 4, and as many as you have patience calculating. So in particular, this included the special case of constant on sequences, which we can think of just as a special case when our polynumber reduces to an ordinary integer. For example, 5 is the sequence 5, 5, 5, and so on. And we had an explicit convention for picking out the kth element of such a sequence. We agreed that this notation here means, so the kth element of the on sequence p of n is by definition p of k, what you get when you replace the n with the particular natural number k. So for example, in this case here, the third element is what you get when you replace the n here with 3. You get 1 plus 3 plus 2 times 27, which I think is 58. All right, so we've got a modest beginning now to studying on sequences. We'd like to now think about how do we go further. How do we extend this to more general on sequences? For example, some of the many sequences found in Sloan's online encyclopedia of integer sequences. All right, so a tempting idea is to try to consider more general ways of generating on sequences by going from polynumbers to more general kinds of expressions. For example, we could try to consider expressions built up from the letter n by not just the arithmetical operations of multiplication and addition and subtraction, but also, say, using exponentiation. So for example, let me just remind you what we mean by exponentiation. So 2 cubed, another notation for that is 2 to the 3. This just means exponentiation. And what it means is 2 times 2 times 2. We're multiplying together 3 copies of 2 to get 8. Similarly, 4 to the 5th, also written 4 with the hat 5. That's 4 times 4 times 4 times 4 times 4, altogether 5 4s. And that turns out to be 1024. All right, so what we're going to think about doing perhaps is to enlarge our expressions, to move from polynumbers to some more complicated kinds of expressions where we allow ourselves to use exponentiation as well as addition, multiplication, and subtraction. For example, we might consider expressions like this, where we have alpha to the alpha plus 3 1 plus alpha to the 2 plus alpha squared. And you could easily imagine building up a lot more complicated things by combining addition, multiplication, subtraction, and also this exponentiation. You could have, of course, repeated exponentiation, the exponent of the exponent of the exponent, etc. So maybe this could be the basis for defining a new kind of object called an exponomial on sequence. Maybe that's a reasonable kind of terminology to go up from polynomial. So for example, associated to this object, we could consider the sequence, or the on sequence E of n, where we replace the alphas with n's. And then this expression is to be thought of as something that's generating integers. The first one obtained by replacing the n with a 1. That would be 1 to the 1 plus 3 times 1 plus 1 would be 2. And 2 plus 1 squared would be 3. So altogether this would be 1 plus 3 times 2 cubed. 2 cubed is 8. 3 times 2 cubed is 24. Add 1, we would get 25. The next element in the sequence would be what you'd get when you replace the n with a 2. In this case, 2,191. And then n with a 3, in which case you get 12,582,939. And kind of obviously, as n starts to increase, it doesn't take long for these numbers to get pretty big, because we've got exponents here, and exponents get bigger than just ordinary products. So this is certainly a tempting direction to go. It's tempting. The question is, does this actually work? This is an idea, but can we actually pin it down logically? It turns out that this is not at all as easy as it might appear from the outside. But before we consider various problems with the idea, let's have a look at some examples. Let's look in Sloan's online encyclopedia and see if we can find some sequences which fall in this category. And it's not too hard to do that. Here's a sort of a random selection that I found. So the 42nd element in his encyclopedia is this sequence here. The numbers 1, 11, 111, 1111, and so on. Just made by strings of ones in decimal notation. And it's not too hard to see that there's a formula for the nth one. 10 to the n minus 1 divided by n. So for example, the first one would be 10 to the 1, which is 10, minus 1, divided by n, which is 9 divided by 9, which is 1. The second one is 100 minus 1 over 9, which is 99 divided by 9, which is 11, and so on. So this is sort of in the direction of what we're talking about. It's basically an expression built up by also having an exponentiation. The n is appearing as an exponent of an expression. Of course, it also has some rational number arithmetic involved, because we're actually dividing by 9. Here's another sequence, which is the powers of 2 plus 1. So 2, 3, 5, 9, 17, 33, and so on, given by the expression 2 to the n plus 1. Now, in Sloan's encyclopedia, sequences often start with n equals 0 rather than the n equals 1 that we're generally working with. That's merely a convention. So for Sloan, the number that would be written here first when we display this sequence would be 2 to the 0 plus 1, which is 1 plus 1, which is the 2 there. So I'll put that in brackets just to indicate that we're actually starting our sequences with n equals 1. The powers of 2, that's number 79 in the sequence. And a more complicated one, the n to the n sequence. 1 to the 1, 2 squared, 3 cubed, 4 to the 4th, 5 to the 5th, and so on. That's number 312. All right, so we've got some examples of such exponomial sequences. Can we do arithmetic with them? It's a natural question. Well, it's not too hard to see that, yes, we probably could. For example, if we have the exponomial e, which is alpha to the alpha, and we also consider the exponomial f, which might be 2 times 1 plus alpha to the 3 plus alpha, then we could say add these two to get that exponomial. We could also multiply them to get that exponomial. And we could do something that we generally can't do with just polynumbers. We could raise one of these to the other. So we could consider something like e to the f. That would be alpha to the alpha to the power f, which is up there. Or equivalently, we could look at f to the e. So there's various possibilities here, and certainly suggestive that maybe there's a kind of a arithmetic with these exponomials. But the question is still, does this actually work? Well, let's have a look at some possible problems that can arise, that will certainly arise. So the first one is that negative exponents generally reflect the operation of division. And division is a little bit more complicated than the other three operations. For one thing, because of the possibility that you might be dividing by 0, which is officially not allowed. So for example, consider this example here. If e is 4 minus alpha to the 3 minus alpha, here we're allowing integer coefficients. Then here would be the corresponding exponomial on sequence, e of n, just obtained from this one by replacing the alpha with the n. Then what would be the sequence that we would want to associate to this expression? Well, if n is equal to 1, then we would get 3 to the power 2, which would be 9. That's fine. And then when n is equal to 2, we would get 2 to the 1, which is 2. Then when n is equal to 3, we would get 1 to the 0. 1 to the 0 is still all right. It can be interpreted as 1. And then the next one would be 4 minus 4, that's 0, to the 3 minus 4, which would be minus 1. So we would have 0 to the minus 1. And something to the minus 1 is usually interpreted as 1 over that thing. So we're really talking about 1 over 0 here, which is problematic with standard arithmetic. So that's one kind of problem that we can expect to have to deal with this more general kind of object. Another sort of related issue is that if we want to extend the values to rational numbers, which ultimately we do, then fractional exponents are undefined. For example, if we want to work, say, with the exponomial 1 plus alpha to the alpha over 3, which is just a small departure from what we're talking about, where we're replacing a coefficient, which is an integer here, with a coefficient which is a rational number. The associated exponomial on sequence would be this thing here, but then the presence of this 3 in this exponent here means that we have fractional exponents. So when we want to evaluate this thing, say at 1, we would get 1 plus 1 to the power 1/3. That's 2 to the 1/3. Well, in our system, we're only working with rational numbers so far. We don't have a cubed root of 2. We've talked about the problematic aspect of things like that. The next entry is going to be 3 to the 2/3. The next entry, when n is equal to 3, will be 4 to the 1. That happens to be all right. But we can kind of expect that most of the terms in the sequence will be problematic for us arithmetically. That's another kind of issue that we're going to have to deal with if we want to work with these exponomials in a kind of a general fashion. Those previous problems that we mentioned, we might be able to get around those by suitably restricting our arithmetic. However, this third problem is a much deeper one and is a serious obstacle to developing a theory of exponomials. It is the non-uniqueness of representation. Let me give you an example or two. Consider this exponomial. It's an expression involving our variable alpha, and it's 1 plus alpha times 1 plus alpha to the alpha squared. Now, if we want the ordinary laws of arithmetic to be valid, this should be the same as 1 plus alpha to the 1 plus alpha squared, because the bases here are the same, so the exponents add. This is really to the exponent 1. So we would certainly want this to be a legitimate equation. But then the question is, all right, well, what's going to be the official name or the official expression for this exponomial? Is it going to be the left-hand side? Or is it going to be the right-hand side? Or is it going to be something different, which is still equal to it. Here's another slightly more subtle example. Consider 1 minus alpha squared times 1 minus alpha to the 2 alpha. Well, this could be rewritten as 1 plus alpha times 1 minus alpha to the 1 plus 2 alpha. That's a little bit more subtle. What I'm doing there is I'm realizing that I can factor 1 minus alpha squared as 1 minus alpha times 1 plus alpha. And I can take the 1 minus alpha from here and sort of group it with these 1 minus alphas, raising the exponent by 1, and leaving this. It's the same kind of idea, but just a little bit more subtle. Go up in subtlety a little bit more. Here's 1 plus alpha to the alpha squared, 1 plus alpha cubed to the 2 alpha, 1 plus alpha to the 5th. All right, well, I claim that can be rewritten like this. It might not be entirely obvious why that is, but it turns out that 1 plus alpha cubed has 1 plus alpha as a factor, and here's the other factor. And 1 plus alpha to the 5th has 1 plus alpha also as a factor, and here's the other factor. So if I take the 1 plus alpha from this term and bring it to here, and I take the 1 plus alpha from this term and bring it to here, then the total exponent up here becomes alpha squared from here plus 2 alpha plus 1. And it turns out that alpha squared plus 2 alpha plus 1 is exactly 1 plus alpha squared. So it's a kind of a rewriting using basic laws of algebra. But it's starting to become obvious that it may not be entirely so clear how to go from one of these to an equivalent expression. I could probably cook up more complicated examples using more subtle and sneaky reformulations that made it quite challenging how to go from the beginning to the end step. And so the problem is, well, if you have these various possible forms for an exponomial, which one are you going to choose? Here's an even simpler example, I suppose. If we consider alpha to the alpha, written with the brackets this way, then laws of exponentiation suggest that this should be the same as alpha to the alpha squared. Okay, fair enough. But now which of these is going to be preferred? You see, when we were working with polynumbers, this did not come up because a polynumber was defined in a very primitive way. It was just ultimately a list of integers. The integers being the coefficients of the various powers of alpha. And at the end of the day, you can take any polynomial or polynumber expression and reduce it to sort of the standard form. So there's never ultimately an argument about what the ultimate standard form for a polynumber is. But with exponomials, this is far from the case. So if you're going to develop a computer program to deal with exponomials, well, then your computer program will have to be very sophisticated, because it will have to be able to distinguish between these various forms and be able to tell whether two expressions are in fact equal or not. So is there a canonical form for an exponomial? Is there some kind of algorithm that detects equality or inequality? Well, I don't really know good answers for these questions. I think they're interesting questions. They're not necessarily insurmountable, but there is certainly some work to be done before we can establish a proper theory of exponomials, and therefore a proper theory of exponomial on sequences. That's just the reality of it. Work has to be done, and that work has to be done before we're really entitled to talk meaningfully about extending our ideas of on sequences to this broader arena. All right, let's change gears a little bit and consider another broad direction that we could go in to enlarge our family of on sequences. Let's introduce the idea of recursive sequences or recursive on sequences. And we'll do so in an informal way at first, because we don't really have a proper definition of these things. Just like we don't really have a proper definition of an exponomial on sequence yet. But we can still start to talk about the ideas. All right, let's start with some examples here. There's some well-known on sequences of this kind that you'll probably be very familiar with. The Fibonacci numbers are the most prominent. They're given by the sequence 1, 1, 2, 3, 5, where every element is the sum of the two previous ones. And we also have to say that the initial elements, which Sloan starts with 0 and 1, are themselves 0 and 1. After that, the recursive formula Fn equals Fn minus 1 plus Fn minus 2 describes how we can get any further element from knowing the previous two. So we can recursively generate more and more terms in this sequence. So these are called the initial conditions, and this is the recursive formula, and this is sort of typical for a recursive sequence, these two aspects. Of course, the Fibonacci numbers, going back to Leonardo of Pisa, traveled through Europe and promoted, in fact, the Arabic Hindu number system as well. A more modern variant of this sequence are the Lucase numbers, which are generated by the same recursive formula, but they have slightly different initial conditions, starting with 1 and 3. So now I'm starting with 1 and 2 as the first two elements. So we have 1, 3, and then the next one is 4, and the next one is 7, and then 11, 18, 29, and so on. There's a slight variant of these where the sequence starts with a 2 and then has a 1 and a 3. That's number 32 in Sloan's encyclopedia. This is 204. So these Lucase numbers have important number theoretical properties. There are many intimate connections between them and the Fibonacci numbers. And they're rather important for primality testing. Okay, so these are two very standard, well-known examples of recursive sequences. So if we widen our view to include these recursively defined sequences, then we get a lot more sequences that are appearing in the online encyclopedia. We get a lot of interesting sequences, and here's another one, number 58, sequence 2, 3, 7, 43, 1,807, and then 3,263,443, and so on. Probably the pattern is not very obvious from that, but here is a description of it as a recursive sequence. The first term is 2, and the n plus first term can be calculated from the nth term by doing the following. We take the nth term and square it, that's the exponent there, subtract the nth term, and add 1. So for example, a0 is 2, so what would a1 be? Well, if we plug n equals 0 here, we would get a1 equals a0 squared, that'd be 4, minus a0, which would be now 2, plus 1 is 3. And the next one would be 3 squared minus 3 plus 1, so that's 9 minus 3 plus 1, that's 7. And then 7 squared minus 7 plus 1 is 43, and so on. These numbers are called Euclid numbers, or sometimes Slyvester's sequence. And they come up in a variety of ways. One very interesting way is the expression of 1 in terms of Egyptian fractions. So the Egyptians worked with fractions, but they were rather fussy about the kinds of fractions that they liked. They only liked fractions with 1 in the numerator. So 1/2, 1/3, 1/7, these were all fractions they were comfortable with, but something like 2/3 or 5/7 they didn't like. So the Egyptians tried to express numbers by writing them as sums of these simple Egyptian fractions. And there's generally lots of different ways of writing a given number that way. So if you try to write 1 as a sum of Egyptian fractions, one way of doing that would be to sort of take the biggest Egyptian fraction that will fit inside 1, and let's say that's 1/2, because we won't include 1/1. So then if we take 1/2 away from 1, then what's remaining has a certain size. And if we look at the biggest Egyptian fraction that we can take away from that, that's 1/3. So if we take that away and then ask, well, what's the biggest Egyptian fraction that we can take away from what's left, that turns out to be 1/7. And so the Egyptian fractions that you get by trying to write 1 as a sum are just those with denominators corresponding to these Euclid numbers. Now there's a very different recursive formula for this sequence, which is that an equals a0 times a1 times a2 all the way up to times an minus 1 plus 1. So for example, a1 is equal to 2 plus 1. And 7 is equal to 2 times 3 plus 1. While 43 is equal to 2 times 3 times 7 plus 1. And 1807 is 2 times 3 times 7 times 43 plus 1. So there's an important lesson here, a rather surprising thing, that recursive descriptions of an on sequence may not at all be unique. In fact, they may be quite wildly different. Who would have guessed that this recursive formula and this recursive formula generate the same sequence? Let's have a look at two sequences that we've already talked about from the point of view of recursive definitions of them. So here was the sequence n squared minus 1, which I associated to this hopping frogs and toads problem. The numbers which are 1 less than the square, so 0, 3, 8, 15, 24, and so on. This turns out to also have a recursive definition, a single initial condition of a0 equals 0, and then the condition that an equals an minus 1 plus 2n plus 1. So for example, that's number 0, that's number 1, that's number 2, that's number 3. So for example, a3 will be a2 plus 2 times 3 plus 1. So 15 is 8 plus 6 plus 1. The famous Catalan number sequence that we've talked about, 1, 1, 2, 5, 14, 42, 132, 429, 1430, and so on, also has recursive formulas, but more than just one. So for example, if we start with C0 equals 1, then here's one kind of recursive formula. What's the meaning of this? Well, the meaning is that let's say we want to calculate what follows after 5. So to calculate this one, what we do is we multiply 1 times 5, that's 5, 1 times 2, that's 2, 2 times 1, that's another 2, and 5 times 1. And we add those all together. So 5 plus 2 plus 2 plus 5 is a total of 14. So 42, for example, is 14 plus 5 plus 4 plus 5 plus another 14. 28 plus 10 is 38 plus the 4 is 42. Quite a different recursive formula is that Cn is actually just a multiple of Cn minus 1. It's 2 times 2n minus 1 all over n plus 1. So again, 14, which is 0, 1, 2, 3, 4, it's the fourth one. So C4, according to this formula, should be C3, which is 5. And what you have to do, you have to multiply by 2 times 2n minus 1. So 2 times 8 minus 1, that's 2 times 7. And we have to divide by 4 plus 1, which is 5. So we have to take 5, multiply by 2 times 7, and divide by 5. That's just 2 times 7, or 14. So the recursive formulas are quite of a different nature. Here we're multiplying by, well, actually a rational function, a polynumber divided by another polynumber. So it's a bit more complicated arithmetically. This one is somewhat simpler, but you have to multiply a lot of pairs of these existing ones. So you need to know the whole sequence up to the point to do the recursion. In this case, you only need to know the last one to generate the next one. And there are other formulas for, other recursive formulas for the Catalan numbers too, of course. So various difficulties have surfaced with the idea of trying to define recursive sequences and to try to set up a theory for them. So amongst these difficulties are, first of all, what kinds of recursive formulas are we going to allow? The ones I've included are relatively simple, but you need to be able to set boundaries to what kinds of formulas you're going to consider. Are we going to allow recursive formulas that are very wordy, ones that involve maybe physical phenomena? The same kinds of problems that we have in defining what exactly a function is surface here. What kinds of formulas are we actually going to allow? How do we tell when two different looking recursive formulas are the same? In other words, they generate what we would like to think are the same sequences. Is there some systematic way of doing that? How do we implement or specify such on sequences on a computer? Well, there's very large range of possible recursive formulas. How are we going to fit them all in some nice little program that deals with these things? How are we going to do arithmetic with recursive on sequences? For example, if we take two of the on sequences that I've mentioned to you, and you have a recursive formula for one and you have a recursive formula for the other. Suppose you add the two sequences, generating a new sequence. Is that new sequence also a recursive sequence? If so, how do you describe it recursively? Is there some way of going from the recursive formula of the two starting sequences to a recursive formula for the sum? Or also the product, or the difference, etc. That's a very knotty problem and not at all easy to answer. And it might only be possible to answer it if we restrict ourselves to rather special or simple kinds of recursive on sequences. So we might only be able to set up this theory by restricting ourselves to rather simple kinds of recursive formulas, at least to begin with. This is an example of the difference between this course and what you find out in the modern mathematical world these days. If you're a student of mathematics at most universities, you will never be told that there is anything particularly problematic with the term recursive sequence. You're just shown a few examples and given some hand-waving description of, well, a recursive sequence is one in which every term is generated from previous ones. I hope you're starting to appreciate how imprecise and vague that really is. Sure, you can give a few examples, but what you really want to do is you want to set boundaries. You want to make it very clear, not just what a few examples are, but what the examples are that fall outside your realm, and where the boundary is between what you're considering and the things that you do not want to consider in your definition. This is much more work than just saying a few words and giving a few simple-minded examples. Okay, so setting up sequences is a lot more work than is generally admitted. And it's work that we're willing to at least contemplate, right? Because our job is to do mathematics correctly. So next time what we're going to do is we're going to be more modest. Again, we're going to start in a simple kind of way. We are going to extend our notion of on sequences, but in a somewhat different direction. A direction which we can nail down very precisely and which is very important for us. We're going to start considering sequences with rational values. So sequences of rational numbers, not just integers. That's going to be crucial for doing calculus and analysis. And Our main tool there is the extension of going from polynumbers to rational polynumbers, where we divide one polynumber by another. That's another rung up the ladder towards a theory of sequences. And we'll be able to also introduce the very important idea of a limit. Of course, without any reference to so-called real numbers. So I hope you'll join me for that. I'm J Wildberger. Thanks for listening.